of in 2D fluids, and in particular about stability of certain stationary solutions. So I will just tell you in general what I mean by stability in this setting, and then I will analyze 3 examples. The Couette flow is sort of the most understood one. And then the Poiseuille flow and the Kolmogorov flow, there are still some things that are unclear, and you know, we will try to see what's going on in this case. So I consider the Navier-Stokes or Euler equations in 2D. So here U is the velocity of the fluid that is supposed to be incompressible, and P is the pressure. And nu is the important parameter of this talk. Is if it's equal to 0, we have an inviscid fluid. So the Euler equations, if nu is greater than 0, we have a viscous fluid, and we have the Navier-Stokes equations. And nu can be thought as inversely proportional to the Reynolds number. So we'll say the inviscid limit is nu going to 0, but it's also Reynolds number going to infinity. I will just use this terminology interchangeably. And in 2D, at least we are in, if we're in the case of domains without boundaries, the very useful formulation is through the vorticity. So omega is the curl of the velocity. That is only one component in this case, so it's just a scalar. And it satisfies the drift diffusion equation that I wrote down here, where the drift is given by the velocity that you had before and can be recovered in terms of the vorticity via the so-called Biot-Savart law. So in the 2-dimensional setting, at least in this setting I'm considering, the well-posedness of these equations is not a problem. The global well-posedness is not a problem. So the interesting and hard question is what's the asymptotic behavior of these equations. So one can think of trying to say something that of the type the Navier-Stokes equation globally evolved towards a certain structure that is most likely chosen by the equation, but this may be a very hard question for the moment. But what one can try to do is instead understand the behavior near some stationary state and some structures that are stationary for this equation. So if we're given just an equilibrium, I'll just go back to velocity formulation for a minute. Say that we're given an equilibrium US. We can write the total velocity as stationary plus perturbation, and we can write down the equation for the perturbation, which is given here. Okay, and and given an initial perturbation, we would like to understand how the perturbation evolves, and for example, whether it goes to 0 or not. This is a reasonable question to ask. And for most practical and purposes, usually linear stability is thought to imply nonlinear stability. So in a sense, one would like to understand maybe better what the linear operator does, exclude the orange term here. And whenever you have a good stability property for the linear operator, maybe you can translate it to the nonlinear problem, because the nonlinearity can be sort of tamed by the linear dynamics. And so one can try to study, for example, linear spectral stability for the linearized Navier-Stokes operator. And this gave rise to a bunch of criteria. I don't want to say too much about this type of concept, but one famous one is the Rayleigh-Fjordhoff criterion that says that if you have a particular solution, a shear flow that is strictly convex, then it is stable. And another concept of stability that most of you are probably familiar with is linear Lyapunov stability, which is good for a lot of reasons, but in this case may lack some stability property as nu going to 0. So this is a consequence of the fact that the linear operators that you're looking at here are non-normal, And you can also see in simple 2x2 matrices that non-normal matrices may behave badly with respect to parameters, their stability, in fact, maybe. So what we're interesting is more of a concept that comes from experimental observation, if you like. And this goes back to fluids experiment performed even by Reynolds in the late 1800s. So if you're looking, for example, in this case, at a fluid past an obstacle, if the Reynolds number is not very high, okay, so if the viscosity is big, then you're in a so-called laminar state where the velocity is a simple form and maybe can be written down explicitly by a formula. And as you increase the Reynolds number or you send viscosity to 0, you may start to see more complicated structures appearing that may possess some stationary or quasi-stationary properties, or maybe statistically stationary if you're interested in that sort of description of fluids. And you may transition to turbulence. So in this case, one can vaguely think of turbulence as an irregular, unpredictable, and chaotic state, okay? So in turn, what this tells us is that stability may be dependent on the parameters, in particular the Reynolds number in this case. And if one would like to prove quantitative stability for such equations, one has to take into account what the Reynolds number is and what is the size of the initial perturbation with respect to the Reynolds numbers. So let's go back to the vorticity formulation now for these equations. So it's easy to see that if you're in the two torus and you consider mean-free solutions, okay, and you just write down the energy, the simple energy estimate with the L2 norm, in this case the entropy, but okay, it's the entropy estimate for the Navier-Stokes equation, then you see that you have exponential decay by rate that depends on the Poincare constant of your domain and viscosity to the power 1. So in particular, there is a natural time scale that is the diffusive time scale, proportional to 1/nu. So to obtain this time scale, of course, we didn't do much with understanding the fine properties of the drift operator. We just used the fact that it's divergence free, essentially. And so to understand the finer properties of the fluids, one would like to understand faster dynamics that maybe happens near stationary states. And so one would like to search for faster timescales, for example, proportional to nu to some power that is minus some number less than 1. Okay, so this time nu to the minus alpha is much smaller than nu to the minus 1. Okay, and so there may be interesting behavior happening in this case. So what is the main question that I want to look at is what is the asymptotic behavior near a stationary structure? And this is the definition of stability that I'm looking at. So say that we're given two norms, x and y, and an equilibrium US of the Navier-Stokes equation. We say that this is asymptotically stable with exponent gamma if initially the perturbation is smaller than nu to some power gamma, then the solution, the perturbation, sorry, will stay small for all times and will converge to 0 as time goes to infinity. Okay. This is a possible definition of stability. Is this in general stronger than the ones that I showed you before? And it's quantitative. This is the main feature here. Because it quantifies exactly whether there is a nonlinear transition threshold, stability transition threshold, in terms of a power of the Reynolds number or the viscosity. So how do we choose these norms, x and y? There is no canonical choice in the sense that there is no good physical reason, for example, to choose one norm instead of another. Usually there is, for y, there is a good norm for the linear problem. So again, the choice is not unique, but there are some norms that behave better with the linearized problem. And so that may be a natural choice. The choice of the norm x, so the choice of the space in which you take the perturbation small at the beginning, is not unique. And in general, the exponent gamma can depend on the space x. Okay, so in this talk, you should think of x as being either a subless space. So I will call these spaces of finite regularity, so HS for S finite. Or you can think of X as being an analytic space. So for example, Gevrey functions, okay? So infinite number of derivatives, and that's infinite regular. And of course, this definition is a bit tailored to the Navier-Stokes equations, but for the Euler equations, when nu is equal to 0, you can think of a statement of the type, if the initial perturbation is smaller than epsilon, then the solution remains smaller than delta for all time, okay? So you don't need viscosity to say anything about this, this definition. Okay, so the class of solutions that I look at are shear flows. So these are just the simplest two-dimensional flows that you can think of, divergence free. They're just non-zero in one component depending on y, and 0 and x. Okay, and if you write down the linearized, the vorticity equation of Navier-Stokes near a shear flow, you end up with the following equation. So there is the nonlinear term here and the viscosity term, they're fine. And then there are two terms arising from the u dot grad omega term. So one is just a drift term, drift by the shear flow. And another one is a non-local term that simply comes up because you have a non-local variation between vorticity and velocity. So in particular here, you see that this is the gradient of omega s, because omega s is v prime, and the gradient of omega s is only one component, is like v double prime. And this is exactly u2, the second component of the velocity by the Biot-Savart law. And these in general, these two terms are not very much comparable in a sense. They interact with each other. And when this is not zero, it can give like also surprising effects in a sense. So non-locality in this equation is not only there to complicate your life, it can also give you something better. And the three cases, as I mentioned in the introductions, are the Couette flow, the Poiseuille flow, and the Kolmogorov flow. So the Couette flow is the simplest flow, and I'll analyze it in the domain T cross R. So for me, X will always be in a periodic setting. Y can be in the whole of R, such as in the Couette flow. And in this case, the red term is not there. And that's an important feature of the Couette flow, because V double prime is 0. But in the Poiseuille flow, for example, same special setting, you will have a term here. And the Poiseuille flow is important because it's the prototypical example of a strictly convex shear flow. Equally important is the Kolmogorov flow, which is instead the simplest example of a flow that is on the periodic in both directions. It is not exactly a stationary solution of Navier-Stokes. You may have to force Navier-Stokes or put the time dependence here. But for the purpose of this talk, let's not get into this. Think of maybe forcing the Navier-Stokes equations in order to have these as a stationary state. So Kolmogorov is also very important and is very good to analyze on a bounded domain. And this is implication, and understanding the asymptotic behavior near Kolmogorov is also an important question in hydrodynamic stability. So let me tell you what happens for Couette flow. There has been a lot of work, in fact, about this flow lately. I'm just gonna mention a few, and but there has been a lot of advancements in the last 1 or 2 years, in fact. So for the Couette flow, if I write down the equation for the perturbation, now it just looks like a drift diffusion equation. There is nothing related to Navier-Stokes at the linearized level. And the beauty of this equation is that it can be solved explicitly in Fourier. So here I call K in a discrete variable, the Fourier variable for X. Remember, X is periodic. And eta is the Fourier variable for Y. And Y is in the whole space, so eta is also in R. And you can write down the equation, and you get exactly this. And these terms, these two terms, will help you understand exactly what I'm talking about in terms of timescales. So let's consider the case nu equal to 0 first. So the exponential is not there. You see that if k is not 0, then information travels to high frequencies. Okay, it's pretty obvious from this term, and this gives rise to a stabilizing effect that you can think of in terms of, say, averaging. Right, the solution keeps maybe oscillating more and more, and averages out. So the stability that you can think about, it cannot be in a strong norm in terms of the vorticity, because, for example, the L2 norm when nu is equal to 0 for this equation is conserved, of course, but it can be thought in a negative Sobolev norm, or if you like, in this case, negative Sobolev norm can be understood in terms of velocity, which is sort of the gradient -1 of the vorticity. So the result in this case is the following, that was essentially established by Kelvin in 1887. So this has been known for, and by Orr, I have to say, in fact, in the early 1900s. So the first component of the velocity decays like 1 over t. Of course, all the modes decay like 1 over t except the x average. What is the x average is exactly when k equal to 0. And we know that for k equal to 0, nothing happens for this equation. Okay, so that's a conserved quantity. The second component of the velocity is automatically mean free in x. And so it has a better decay 1 over t squared. Okay. But the point is that you have a quantitative linear stability property for these equations that is given essentially by vorticity mixing, i.e. from this term. When nu is greater than 0 instead, you can quantify timescales in terms of inverse powers of nu. And because this integral contains a tau square integrated in is like t cubed here, it's not hard to see that everything but the 0 mode, the x average of the solution decays extremely fast. So you see here, I don't have nu t, I have nu t cubed. So this is an extremely fast decay that comes from the fact that you have mixing interacting with viscosity. Okay, this is a simple computation, and the important thing that you have to keep in mind here is that there is a time scale that arises here that is proportional to nu to the negative 1/3. Okay, which is much faster than the diffusion time scale. So what is the nonlinear result? So how do these estimates translate into the nonlinear result? Let's see. So one would like to say that for small perturbation, the perturbation u to the Navier-Stokes equation converges back to a shear flow. So why? Well, if you could just translate these estimates to the nonlinear at the nonlinear level, the second component goes to 0. The first component goes to 0 except for the x average of it, which is a y-dependent function only. And so it's a shear flow. Okay? And so can this be proven? That's the question. So in general, you would like to take a small perturbation in space X. And there was a very nice work in 2010 by Lin and Zhang that said that this statement is essentially false if X is of low regularity. So in fact, they proved that there are steady states in H3 minus epsilon near the Couette flow that have cat-size structure in the sense that they have non-trivial X dependence. So in particular, they're not shear flows. And so if you start with a perturbation that is at epsilon distance in H3, then you can never, in general, converge to a shear flow because you may hit one of the stationary structures. This is, in fact, in their paper is sharp, and they show that this cannot be done if you take bigger regularity than H3. Okay, so however, Jacob Bedrosian and Nader Mazmoudi in 2013, they proved nonlinear asymptotic stability for the Couette flow if you take the space X of infinite regularity, so Gevrey 2 minus epsilon. Okay. And this space, Gevrey 2 is essentially optimal by work of Deng and Mazmoudi. So there's been a lot of work recently about extending this type of results to shear flows that are not Couette. And there's been some work by Mazmoudi and Zhao and by Ionescu and Hao Jia, in which they proved that also shear flows near Couette undergo this type of behavior, this inviscid damping behavior. But I don't have too much time to talk about those right now. What about the nu greater than 0 case, so the Navier-Stokes equations? Well, again, if you take X to be infinitely regular, so Gevrey 2, Bedrosian, Mazmoudi, and Vicol proved that the exponent gamma that you need here is 0. So essentially, you have the properties at nu greater than 0 and nu equal to 0 are stable in the limit nu going to 0. Okay. This, if you take infinite regularity. If you take finite regularity, then Bedrosian, Vicol, and Wang, they proved that gamma is 1/2. If you take, say, HS for S greater than 1, you expect this gamma not to be 0 because of the result of Lin and Zhang, for example. So it's not possible to have a stable a stability threshold that is independent of nu in that case. And this was improved recently by Mazmoudi and Zhao to 1/3, essentially for a finite regularity space. Okay, so for the Couette flow, the type of results that I told you about can be proven. And in these idealized concepts of no boundaries, but there has been work also with boundaries and so on. I don't have time to go over that. And also in 3D, there are some very, very interesting works in this sense. So what about more complicated flows? So for the Poiseuille flow, if we take y square, we do have the non-local term. So the linear problem becomes harder to analyze. In particular, it cannot be solved explicitly in general. But again, the importance of this flow is that it's strictly convex. And the non-local term here, even though it appears, it is antisymmetric with respect to the L2 scalar product, as is the blue term. Okay, so this is an important feature. In general, for a strictly convex shear flow, you have to weight the norm by 1/u double prime, but in this case, you don't. So there is some analogy with Schrodinger equations in this case. So if you like to take the Fourier transform in both x and y in this equation at the linear level, so I'm neglecting the nonlinearity, you do get a Schrodinger type equation. It's a one-dimensional Schrodinger equation depending on this parameter k that is non-zero, is an integer, and eta is the only variable that you have. And if you have viscosity, you also have a complex potential. There are some works in the case nu equal to 0 for the whole space about Schrodinger equation that tell me that there should be implicit damping. However, I'm not so sure that one can prove exactly the statements that I told you about Coette just by relying on the Schrodinger formulation. There are some other works that obviously don't use Fourier methods in Y in the sense that you don't Fourier transform the equation in Y if you work on the finite channel. So there is a nice work by Wei, Zhang, and Zhao in 2017, which they prove linear implicit damping for this flow. And as I mentioned, in the whole space, there are some papers by Schlag that I think are very relevant to this problem, but my ignorance in Schrodinger equations probably doesn't allow me to get the full result. But this is a nice parallel between damping in fluids being some sort of related to dispersion in a sense. Okay, so how do we prove enhanced dissipation? Instead, the viscous problem in general can be maybe slightly easier. And we analyzed this with Tarek El-Guindi and Klaus Wiedmeyer in 2019 by using so-called hypocursivity techniques. And you can prove that the vorticity decays like nu to the 1/2, e to the minus nu to the 1/2 t, in a space X that is essentially L2 weighted because you need some way to take care of infinity that just comes from essentially from the derivative of y square. That's all you need. Hypercursivity requires certain commutators that give rise to this norm very naturally. The point is that there is a faster time scale. And so at the linear level, and so the question is, what can you say about the nonlinear level? Well, at the nonlinear level, you can say that if the initial vorticity is less than nu to the 3/4, so gamma here is 3/4 for me, then the same estimate holds true for the nonlinear level. And the x average of the solution, which is not expected maybe to decay as time goes to infinity, remains small as the initial perturbation. Okay. Let me say that 3/4 may not be sharp at all. It is in a sense sharp if you only rely on the enhanced dissipation estimate that I have. The problem is that I don't know implicit damping for this equation. So if I knew implicit damping, I could prove maybe a better estimate here. So, but I cannot treat the nu equals 0 problem in the whole space. Of course, Wei, Zhang, and Zhao treated in the finite channel, but in the finite channel, if you look at vorticity for Navier-Stokes, then you have the problem of boundary conditions. So there is sort of a balance here in complications, in a sense. Okay, so what are the key elements of the proof? So the main features are that this equation decouples in the x frequency. So if you take an x Fourier transform, you just get a system of infinitely many equations depending on k, the x Fourier variable. So this is important, but we don't want to use the Fourier transform in y. And instead we use hypercursivity, which was, say, popularized by Villani with his memoir in 2009, and used for, say, the first time in the context of Navier-Stokes equations near shear flows by Beck and Wei in 2011. This relies on, say, slightly more complicated energy estimates than the basic ones, which take into account commutators between the antisymmetric parts of the equations and the symmetric part of the equation. So the goal would be to construct a functional that controls the energy norm that I want to have enhanced dissipation in, and satisfies a good Gromval estimate of the enhanced dissipation type. So it does satisfy a better estimate than the L2 norm, for example. So the energy functional here is this one. And in the next slide, I will tell you why this is sort of a natural energy for this problem. So it just involves the L2 norms and the H1 norm, and then some terms arising exactly from commutators between diffusion and antisymmetric part. So let's, I'm writing here the linearized equations. So if you just take the L2 norm, you get the energy equation. That's not hard. If you take a gradient of the equation and then you take the L2 norm of that, then you get the following. And here I get 2y dx, and 2y dx is exactly a commutator. It's a commutator between dy and the antisymmetric operator. And this is what goes on here. And what Villani tells you to do is, well, take another time derivative of this cross term here that doesn't have a sign, but it was included in the functional before. They take another derivative, and the good thing is that you create some good terms. So this term has a good sign. This term is, in a sense, surprising. In general, shouldn't have a sign for, say, general convex shear flows, but it does in the case of the Poiseuille flow. And then you have some error terms that depend on nu, and this is okay because nu is small and maybe those can be controlled. So then you would have to take another time derivative of what the commutator is. So if you take the time derivative of that, well, you get some good terms, maybe a bad term here, but it has a nu in front. And then another term, a red term, that is very scary in the sense that it doesn't have a nu here. It's true that it's low regularity, but believe me, it's not controllable by what you have in the other, by the positive terms that you have in the other equations. Where does this term come from? It comes from the fact that, okay, once I take the first commutator, then I will have to take a second commutator, again, between the first commutator and the antisymmetric part of the equation. And this is not zero. It's explicit. It's exactly this, but it's not zero. And believe me that if you then take the second commutator and you hit again with the antisymmetric part of the equation, because you have a dy here, there is going to be some term arising from y squared. So no successive commutator will ever be zero. And if you look at the Villani memoir, for example, this would mean that you have to build up a bigger and bigger energy function. And this is not just not practical. However, there is a hidden identity for the Poiseuille flow that comes from taking the gradient of the dx of the stream function. And in particular, it produces a term that is exactly the same as the scary term there. And so you can combine these two equations in a reasonable way, multiplying this by 2 and adding, so that you get rid of the error term. And incidentally, this also gets rid of this term because you have exactly the same term here. Okay, this is sort of coming from the velocity equation, if you like. And it's a very special structure just for Poiseuille, in a sense. Okay, so once you have, so if you combine this in a sort of complicated but doable way, this whole equation, you can in the end close a good Rhombus. So once you have the linear equation, then you can try to apply some sort of Duhamel type argument to bootstrap this to the nonlinear case. So here it's you have to think of just the shear part of the solution and the non-shear part of the solution, and you come up with just a norm that encodes the linear decay. And the bootstrap procedure that you would like to encode is that, well, if your perturbation is of a certain size in this norm, then you get a good control of the nonlinearity, and then you iterate this control in terms of the perturbation omega tilde. And the steps is simply that you can get some energy estimates provided that for your equation, provided that the perturbation is of size 4c0, and you can prove that this estimate propagates with even a smaller constant. And so t can be extended essentially to infinity. Okay, so this is more or less what we know about the Poiseuille flow. Let me go to the Kolmogorov flow, which is the most recent work that I've done so far. So in this case, let me write down again the Navier-Stokes equation near the Kolmogorov flow. And there is a special structure here because v double prime is minus v in this case. So you can group the local transport term and the non-local term in this way. And we consider this equation on a torus, not just square, but of size, it can be potentially rectangular, okay? So it's stretched in the x, sorry, in the y direction, if you like. It's small in the x direction. And there is a point in considering L equal to 1 or L bigger than 1 because the behavior is actually very different. So in the case L greater than 1, there was some preliminary work by Zhu, Lin, and Xu about linear and nonlinear enhanced dissipation without rates. So one can say that, well, there is a faster decay rate than the heat equation rate, but no rates were provided. And the rates were provided by Wei, Zhang, and Zhao in the case of rectangular torus, both in the inviscid and the viscous case. So in the inviscid case, one has a linear inviscid damping rate that is the same as the Couette rate. This is surprising in a sense because sin y can have critical points, of course, and so critical points may slow down the rate. This is true if you consider the equation without the non-local term, but amazingly enough, for the Euler equation, the rates are exactly the same as in the monotone case. And this is what I was saying before, that the non-local term does give you something more. It's not just a lower order perturbation that you just have to control. The linear enhanced dissipation rate is the same as for Poiseuille, nu to the -1/2, the time scale. But the transition threshold is better. Nu to the 2/3 is a better threshold than nu to the 3/4 that we had before. And this is because Wei, Zhang, and Zhao, they can prove also linear inviscid damping. So that's a very important property of this equation. The nonlinear statement is then the same in a sense. I mean, the conclusion. Okay, so this was later simplified by Wei and Zhang, proving the same linear estimate via hypercursivity. So similar strategy as in the Poiseuille case. Now, what happened? This is for the rectangular torus. What happened for the square torus? So the point is that in the square torus, 1 plus Laplacian to the -1 has a bigger kernel as some kernel, in fact. So This was addressed in a paper by Beck and Way in this case, without the non-local term. So there is, if you just consider passive scalars, then you do have linear enhanced dissipation at the scale that you expect, nu to the negative 1/2. Lin and Chu also proved that you either have enhanced dissipation or you have growth of anomalous modes. And there were no rates in this case. And the anomalous modes, you can think of them as generated by the kernel of this operator. And the quantitative breakthrough was essentially done by Ibrahim, Aikawa, and Mahmoud in 2017, which they proved linear enhanced dissipation at rate nu to the -1/2. And more or less at the same time, Wei, Zhang, and Zhao in the paper I mentioned in the previous slide also proved linear enhanced dissipation at the same rate, and also Inviscid damping. So, and the hypercursivity proof of Wei and Zhang works also for the square case. So in the case L = 1, essentially it's similar behavior as the rectangular torus, except that you have to take into account that you may have more non-decaying things because you have some kernel. Okay, but by projecting the linear semigroup in the right way, then you can do this. However, the main difference is that there was in none of these works there were any transition threshold for the stability, for the nonlinear stability, and this is the main difference. So, what is the obstruction to nonlinear result is essentially the fact that this operator, which is the antisymmetric part of the linearized operator, has a bigger kernel in the square torus than in the rectangular torus. So in the rectangular torus, the kernel of this operator is just functions of y, because you just have a dx in front. But in the square torus, you have also sine x and cosine x. So the first eigenfunctions of the Laplacian, the first shell in x in frequency. So the idea is that maybe one can use the richness of this kernel to construct structures near Kolmogorov that are stationary for Euler. They are non-shear, so they have this cat-sized structure, and they're smooth. Okay. So this may remind you a bit of the work of Lin and Zhang for the Couette flow, in which the structures that they found were H3 halves in vorticity. Okay, so here we aim at do things more regularly. So this is the recent work of myself, Tarek Akindi, and Klaus Widmeyer. So we proved that there exist analytic stream functions, psi epsilon, that are stationary solutions to the Euler equation. So all functions that satisfies an equation of this type are stationary solutions to Euler. They are close to the Kolmogorov flow. Here I write H2, but in fact it can be in any norm. It's just how regular the perturbation is from cosine y, and it can be analytic. So this doesn't have to be H2, it can be anything. And they have cat-sized structures. So psi epsilon, if you test it again, something that is not in the first shell, frequency shell in X or Y, but it is in this case in the 1,4 mode, then it gives something that is order epsilon square plus smaller contributions. So in particular, there is some non-trivial X-Y dependence in these structures. Okay. So why do we get analytic? Well, the strategy of the proof essentially constructs H2 functions that satisfy this equation, but F is just a polynomial of degree 5. So by elliptic regularity, this just bootstrapped to analytic right away because you have an analytic nonlinearity. So the corollary of this is that there cannot be nonlinear implicit damping for the Kolmogorov flow in the square torus, no matter how regular you take the perturbation, okay? You cannot take even analytic perturbations because you may hit one of these stationary structures. So the idea okay, so this is, I'm sorry, can I go back? Okay, so this is an immediate corollary at the Inviscid level, because you just found stationary structures for Euler, and so there is nothing that can damp, at least to a shear flow near Kolmogorov. What about the viscous case, Navier-Stokes equation? So the idea is that you don't want to enhance dissipate to something that is just in the first frequency shell in X, or is just Y dependent, okay? So the result is the following. So assume that nu is small enough, and you can find an epsilon. So if given nu positive, you can find an epsilon such that the stationary structure that I constructed is order epsilon squared in this space. And but by the time scale of the heat equation, if you start Navier-Stokes equation with that function that I constructed, it remains of the same size. So if this solution underwent an enhanced dissipation, this quantity would have to be extreme arbitrarily small if you take nu small by the heat equation timescale, okay? Because it would decay, say, like e to the minus nu to the 1/2. So everything that is projected away from the kernel of the operator that of the linearized operator should just become very small, and in fact it doesn't. So there is also not a possibility of a transition threshold, and in particular this just says that the Kolmogorov flow on the square torus is really not very stable at all, either for Euler or Navier-Stokes at the nonlinear level, despite the fact that it is linearly stable, okay? So I think this is really interesting. Just 2 words about the proof. So the goal is to find stationary solutions for Euler that are close to the Kolmogorov flow. So the Kolmogorov flow, I call it psi star because I will do some manipulation on it. It's just cosine y in this case because the velocity is sine of y. So the idea is perturb away from psi star by constructing a perturbation of the f and a perturbation of the psi. So of course, Kolmogorov satisfies equation 5, and we just make the ansatz that the capital psi that we're looking for is psi star, the Kolmogorov solution, plus epsilon some perturbation. And similarly, the function f is just f star, the Kolmogorov function, plus an epsilon perturbation. And psi and f are to be determined. So what do we have to pay attention here? So if you just plug in this and this back into here, you come up with the following equation. So you have to be able to solve for the perturbation Laplacian of psi plus psi equal f of cosine y plus epsilon cosine x. These can always be added to the perturbation because it's in the kernel of the operator on the left. And then you have epsilon psi. So you would like to solve this, and you would like to avoid, you would like that f avoids the kernel of Laplacian plus 1. So it turns out that choosing polynomials of degree 5, it's fine, in the sense that you construct polynomials of degree 5 that have coefficients that can also be expanded in epsilon. And you can close at every epsilon level, you can find a form of F that is feasible. And then you close a contraction argument essentially to prove existence of this nonlinear problem. The choice of a quintuple polynomial is completely arbitrary. We need to have some freedom in choosing the coefficients, so we cannot just have a quadratic function, for example. And we choose something that has degree 1, a degree 3, and a degree 5. So we avoid the even terms of the polynomials. But this is essentially for convenience. It's not that essential. But this indicates that there are many other possibilities, and there is essentially large families of such structures. In particular, you can always add to this polynomial an epsilon square polynomial, and it's going to be fine. So again, analytic solutions is not a problem because you just find it from elliptic regularity. And the main thing that helps here is that the heat semigroup leaves the kernel of 1 plus Laplacian minus 1 invariant. So this is a very particular feature of Kolmogorov in the sense that this operator just arises because we have Kolmogorov flow here. Okay, so I think I'll stop here. Thank you very much.